Okay, so welcome everybody to today's webinar. So the subject of today's webinar is going to be post-molding simulation within SIGMASOFT. Okay, so right now all the lines are muted, and we will, as we normally do, we'll go ahead. I'm going to go through the presentation. At the end, I'm going to just show a couple things actually inside the software, and then we'll take some questions. So my name is Phillips, and I'm based in Phoenix, Arizona, and my information is down at the lower right-hand part of the screen. So if you want to contact me after the webinar with any specific questions about any of your projects or would just like to talk, please feel free to do so. Okay. All right, so post-molding simulation. So if you're attending this webinar, I'm going to assume that you've had some exposure to SIGMASOFT thus far, because this is a topic-specific webinar, and just like some of the other ones we've done, we did one on analyzing the entire mold, did one on multi-cycle analysis, even did some simulation setup demos to show the ease of meshing. So this is another one that a lot of people have asked about, so post-molding simulation. So we're going to talk about today what is it, why is it important, when you should use it, how does it impact the results, and what is required to set up an analysis. Okay, so what is post-molding simulation? So you probably can guess, but I'm going to go through. So your typical injection molding process, of course, is you go through some sort of filling phase, typically velocity controlled injection of the polymer into the cavity through the runner system. And then you switch over into a packing holding phase to compensate for shrinkage and even allow additional polymer to be, I guess, pushed into the cavity to, again, offset the shrinkage that's occurring and the shrinkage, to compensate for that. And then we move into to a cooling phase at some point, typically after your gate freezes, ideally, and hold the mold closed for a certain period of time until that part is ejectable. And every polymer has an ejection temperature, so we want to reach some sort of temperature we can eject that part. Typically, it's still hot when we eject it because we want to have the shortest cycle time possible. So typically when we eject the part, it's still hot, and even if you have some thicker sections, if you actually cut that part open, some of those thick areas inside of there would be really warm. And really, so that's the goal here today is what happens after ejection. So once that part is ejected from the machine, it continues to cool to ambient temperature. So every area of that part is completely cool, and the idea, of course, is what happens during that phase. So as that part continues to cool, there's additional crystallization that may occur if it's a semi-crystalline material. Additional shrinkage and warpage may be occurring, and mold and stresses are going to be changing as well as those temperatures change and the part continues to cool. And then also in some cases, is there some sort of a secondary heating or cooling process that's happening in the real world? Are you dropping the parts into a water bath or something like that, or applying heat to it? So the idea with SIGMASOFT, of course, is that we can simulate this, and really the idea that the reason I think a lot of people are asking this question, and the reason I want to talk about it today is because this is something that other polymer simulation packages do not account for, and this is really what makes us kind of a leap ahead in terms of accuracy. Is that if you run your analysis and you're just looking at, say, warpage at ejection, you're not really getting the true picture of what's happening in reality. And I've been working in the simulation industry for over 13 years now, and I've seen many, many cases where people have used analysis and they've seen it's predicted a certain amount of, say, warpage, and then they rely on that. And then, of course, when they actually in the real world, the part comes out of the machine, and sure enough, it's pretty close. But then it sits in that conveyor belt for 10 minutes, and they see a completely different picture of what's happening, and the part continues to warp. And, of course, they didn't expect that. So, again, with simulation, and the more closer to reality we can get, right? So, of course, why use this? So I think it's pretty simple, right? Accuracy. We need to be more accurate. So here's just an example. If we look at distortion at ejection, and then even after 6 minutes, and then after 1 hour when the part is completely cooled to ambient temperature, you see a pretty drastic difference in temperature here. We went from 77 thousandths to 365 thousandths just in that 1 hour period. I'm going to get into some more examples just like this today. Then also, look at crystallization. So another, I guess, benefit of SIGMASOFT is that we actually consider crystallization in our calculations, which again is very, very valuable and very important because this happens in the real world. So we can look at crystallization, and of course that's going to have an impact on density and on warpage and shrinkage and stresses in the part. So we can look at that at ejection. But in reality, if you look at the example on the screen, we get a drastic difference after 1 hour when that part is completely cooled in terms of how much that part is crystallized. Okay, so what is required in SIGMASOFT to do this? This is probably one of the easiest things to set up in the analysis because really all you have to do is specify a time and then at what time steps you want to output your results. So here's just a snapshot from the software where I have the external cooling, a window pops up, you just specify I want to cool it. In this example, we're going to cool it for 1 hour. But you could do this for 10 hours, for 24 hours, for as long as you want. But you typically see the most benefit in that first 30 minutes or 60 minutes, maybe 75 or 90 minutes, because most parts will cool within that time period. The longer time frames, of course, would be valuable if you're doing any type of tempering. So as I mentioned, if you're going to apply some sort of heat or cooling to it after it's ejected, you can do that in the software as well. So we would check that tempering box there, and then specify, what temperature it's subjected to over what period of time, or some sort of profile. And then once we do that, as I mentioned, then we just want to pick our time steps. So we can specify at what outputs we want to have the times, and then at what time steps we actually want to output specific results. So in this case, I have outputs, every 10 seconds, and then as I get longer in, I might go every, 30 seconds or 60 seconds. And then at the bottom here, I can actually pick, a whole bunch of different types of results that I want to see, not only right at ejection, but also, like I said, at all these different time steps as the part continues to cool. So we can look at, of course, displacement, which would be your shrinkage and warpage, probably the most common result, but also stresses and strains, and all kinds of different, as you can see on the screen, different types of results that we can look at in the part. Okay, so I'm going to go through a few examples here. So the first example here, and a few of these are the same part, but I've tried a couple different materials. So here we have just a talc-filled polypropylene, and at ejection, we see, of course, as you would expect with a box, we have a certain warpage that's occurring here, where both sides are warping inwards. So we're looking at displacement in the x direction. So if we look at a negative x here, we have this 179,000 pushing in, and then of course 177 pushing the other way. And I've left the gate on the screen just so you can see where it's injected. So in this case, we're looking at the flow direction. So just after 25 minutes, our part actually reaches ambient temperature, and you can see that our warpage has actually increased 125%, in just that 25 minutes. So drastic difference here. If we look at the cross-flow direction, same idea. So we can measure the amount of displacement on the one end and on the other end, and then take that distance and the difference compared to the part length. And then here we're actually looking at it in the cross-flow direction. Our warpage has increased by 276% just in that 25 minutes. And I've used the same scale on the right side just so you can see, so the colors will show that difference graphically. Okay, so I'm going to go ahead and animate this, and I actually have the distortion turned on as well here. So this is actually animating the distortion from ejection until the part completely cools. So this is actually what's happening on your part as it sits there on a table or on a conveyor belt. And let me go ahead and animate this again. And I have this scaled 5x just so you can see more of the magnitude. Okay, so another thing I want to point out here is that I mentioned the crystallization. So we're going to calculate crystallization during the entire process. So here what I have is I've actually sliced apart. And the idea of what I've done here is I wanted to slice it so we can see through the thickness as well. Because as you can imagine, what's happening inside is a little different than what's happening at the skin. So right now what we're watching is the crystallization through the entire packing phase and the cooling phase. I'm going to go ahead and stop this. So the more yellow, orange, red that it becomes, the more it's crystallizing. So we can see, we have like 67% crystallization here in the red, whereas the blue is where it started, 1%, 5%, so very low crystallization amount. And here, so if I look at my time step here, so we're about 6 seconds into the packing. Actually, our packing time in this case is 7 seconds. So we're almost at the end of packing at this phase. So actually I can go one more step here. So we're right at the beginning of cooling. We've turned off our packing. Now we're just holding the part in the machine. If we look at our crystallization here, you can see that we have no crystallization here in these hot areas, of course, because they're still completely molten. They haven't hit that transition yet. Let me go ahead and animate this further. As the part cools, so you get a higher degree of crystallization there now in those areas. So another thing I would like to point out, though, is that after 1 minute 6 seconds, our crystallization stops. So in this case, we have a cycle time of about 30 seconds. So it's actually 36 seconds. And the idea here is this part actually is done crystallizing almost right at ejection, or just maybe about 30 seconds after ejection. So that difference that we saw in our warpage actually is not too much relied on a crystallization, because our crystallization actually is completed almost right at ejection, or just a few seconds after ejection. So we can look at other things. Okay, so what else is occurring? So in this case, we're actually looking at our stress increase after the part's ejected. So we're looking at von Mises stress in this case. So I'm going to animate it again. So this is actually the final stress in the part. So I have it now at 1 hour, 1 hour and 26 seconds after ejection. But actually, in reality, the stress is actually stopped around 25 or 30 minutes. I just have this one last time step. So I'm going to animate it again. So the beginning is actually the stress is in the part right when it's ejected. So if we look at it right here, so we can see, we have pretty low stresses. So that if we look at the color scale, we're probably right down here around the 4 or 5, area in terms of megapascals, in terms of von Mises stress. And right now we're 56 seconds. So we're about 20 seconds after ejection. And this is going to continue to go. So we have 30 seconds. 2 minutes, 3 minutes, 4 minutes, 5 minutes, 10 minutes, 20 minutes. So you can see there that after ejection, we've output those results at different time steps. And again, that's a drastic amount of stress difference. You go from these areas where here we had 50 versus here we have more like 5. And as anybody would know, if you got a highly critical part in the real world, that when you're going to put it into application, you'll have a better idea what those stresses in the part are. But also, these stresses are going to impact that distortion. So you have tensile stresses and compressive stresses in different areas that are going to create non-uniform shrinkage that are going to cause that warpage and shrinkage. So the stresses that are changing over time are also the resultant in there, of course, you're seeing is that warpage. Okay, so same part, but in this case, I'm actually switching over to PBT. So that's a 30% glass-filled PBT. So we have a little bit less warpage in this case, but we also have different, because we're in the flow direction, now we have our fibers, and then we're, of course, in the cross-flow direction. So the fibers are going to have an influence here. But if we look at our displacement at ejection, and then again, after, in this case, it took about 1 hour to reach ambient temperature. And here we have our warpage increased by 261%, so drastic increase. If we look on our cross-flow direction, our warpage is increased by 600% in that 1 hour. Drastic difference. So we've gone from 0.02 to 0.095. Okay, so then another example here. So different parts. We took an unfilled cycloid material, and again, so if we look at our warpage here right at ejection, so we're about 650 thousandths. I'm sorry, 362 thousandths, and then over here 656 thousandths. So our warpage is actually doubled in just 10 minutes. So if we look down here, we can see our time is 600 seconds. And then over here, of course, our time was 23 seconds. So at ejection, this is a 23-second cycle. And then if we went, basically 10 minutes later, you can see a drastic difference in the amount of warpage that occurred. Okay, so in summary, if we consider the entire mold in the process, so this is kind of talking about some of the things we've already talked about in some of our webinars. So with SIGMASOFT, we just get closer to reality. So we allow you to consider all the mold components, the entire process, consider multiple cycles, take into account viscoelastic behavior, the material, and the crystallization that occurs. And then what we talked about today, what happens after ejection. So by doing all of these things that people typically in the simulation world are not used to doing, we get a much closer snapshot of reality. And if we do this, of course, we're making better decisions because we have better results better data to make our decisions on, which is going to lead us to better accuracy and better part quality. And of course, we can understand what is happening during the complete cycle while the part's in the mold, and also what happens when it's ejected from the mold. And and the idea with simulation, as always, accuracy matters, and as much as we can do to simulate the design and process to reality, the closer we're going to get. Okay, so at this point, what I would like to do is go to the software, and I just want to show just a little bit of the software. And I like to do this. I've kind of hit all the points I wanted to hit through the PowerPoint, but I always like to go into the software just to show a little flavor of what the interface is like and what it looks like. So here we actually have different results. So I'm going to go into my so I have my stress results, of course, is where I had my displacement and all the different time steps that we mentioned there. And the X, Y, Z, you can see we have the different time steps, and of course all of our filling results as well. So in this case, what I actually want to do is go into my cooling, and I'm going to turn on my X-ray mode, which actually allows us to see through the part, or transparent view. Then I'm going to go to my temperature. So in this case, I ran 15 cycles. So I'm going to go to my 15th cycle, of course, because that's where all my results are going to reside, or my most important results, I should say. Okay, so if we look at our process here, so if we look at, I'm going to go right towards the end of packing. Okay, so look at the temperature of the part. We can see here that, we could just basically one snapshot of temperature, right? And then, so what I want to do is I actually want to go in here. Now, the ejection temperature for this material is 115 degrees C. So I'm going to actually, all I want to do is I want to show everything that's above 115. Apply that. So what this is going to do is really show me all the areas of the part that have gotten to a point temperature-wise where they're ejectable. So at the end of packing, you can see here that my part is still pretty hot. I got areas that are well above 200 degrees. Probably my average temperature is somewhere sitting around 140 or so. But the idea here is that I want to go really into my post-molding results. So at ejection, so I'm going to go ahead and click here. This is what the temperature. So these are all the areas of the part that are still above that ejection temperature. So I'm ejecting at this point, but as you do in the real world, you can see that actually it's really inside the core of these thick sections. So basically these big thick ribs. I can see that some of my polymer there has not really reached that ejection temperature yet, but that's okay. But as you can imagine, what's happening, after ejection, right? So if we go to 10 seconds after ejection, okay, of course, and as it starts to disappear, basically it's solidifying. So if I go to 20 seconds after ejection, you can see it continues to 30 seconds. So as you can imagine, in these areas, we're going to have a chance for voids, a chance for sink marks, and so forth. And I probably could even hold this part in the mold a little bit longer. Even if I look at this, it looks like I still have a little bit of material on the outside of that rib. So this tells me that when I go back, I probably need to rerun this analysis and have a little bit longer of a cooling time. But that's part of the benefit of analysis, is determining your cycle time. So in this case, I actually can get a very dead-on depiction or prediction of what my cycle time is going to be. So right now, I've tried to eject it after 26 seconds, and it's saying, you know what, you probably need to eject it maybe more after 40, 50 seconds. So that way, at least I understand my cycle time. So let's go to 1 minute now. And then like I said, you can go back through here. I can go to 2 minutes and see pretty much there we're almost gone. Now you might be asking yourself, say, well, after 2 minutes, it looks like everything's ejectable, but we're looking at everything above 115 degrees, so we still have some pretty hot areas here. So if I go back to my X-ray mode, I'm going to go back now, and 23 degrees would be our average ambient temperature, right? So this is what my part is actually. So I'm still well above my ambient temperature for the entire part. So at this phase, I am actually 2 minutes and 36 seconds. So my part has been out of the mold for 2 minutes already, and this is still the temperature of my part. I can go in and and query some of these values. So 84 degrees, 91 degrees within there, even sliced apart, and go through this rib here and see. Okay, so I'm still 122 degrees in the center of that rib. So let me get back to my results. So now I'm actually looking at the part to see, when is it completely cool? When does it reach that ambient temperature? So as you can imagine, right now what's happening is the stresses in the part are changing. It's continuing to cool. It's continuing to shrink. It's continuing to basically change shape. And that's what that's the whole point. So after 4 minutes, so I'm going to just go down here and go, okay, let's go right to 10 minutes. Okay, so after 10 minutes, now we see some of our part is actually completely solidified. And if you look at this part, it makes sense because this wall thickness here is 2 millimeters. This wall thickness over here is 1 millimeter. So we have a much thinner wall, which makes sense. That's why it's solidifying. So let's go to 15 minutes now after ejection. So now we're actually really starting to see the part solidify. So let's go to 20 minutes. All right, so 20 minutes, really now we just have this one area here. So we're still getting additional shrinkage, additional displacement, stresses are changing in that area. And as I showed earlier, our crystallization has actually stopped. Go to 25 minutes, and boom. Now everything is completely cooled to room temperature. Now I typically apply, so I've gone 30, 35, 40. I've applied some additional time steps here just in case. Like I showed you that one example with the PBT where it took an hour. So I typically always do an hour. And then at least I can always say, well, really at 25 minutes is when it's solidified. But I want to make sure I capture that time step. And then, of course, in the PowerPoint I showed you at 25 is when our displacement finally stopped changing. Okay, so with that, I'm going to go ahead and just go to my summary slide here, and then we'll take some questions. So I have my information on the screen again. And I do want to point out, too, that so this is the last webinar we've done in this series. So we started this about 7-8 weeks ago. So we have recorded versions of the webinars that are now on YouTube. So we have an introductory webinar that's the overview of some of the real big capabilities and differentiators with SIGMASOFT, why we are the technology leader. There's a simulation setup demo to show how to bring models in and mesh them and get into the analysis. And then one on the benefits of multi-cycle analysis. So that one actually is being posted today, so it should be on later in the day. And then, of course, this one we'll go ahead and post as well. So if you need these links to any of these or you can't find them on YouTube, definitely send me an email and I will get you hooked up. Okay, so let me go over here to the question area.